Welcome to Chapter 3 of our Bayesian Optimization series, where we explore acquisition functions. These are the strategic decision-making components that determine where to sample next in our optimization process. The core challenge is balancing exploration of uncertain regions versus exploitation of promising areas, and acquisition functions give us principled ways to make this trade-off. Acquisition functions are the heart of Bayesian optimization. They take the mean and uncertainty predictions from our Gaussian process model and convert them into a single score that tells us which point to evaluate next. They serve three key roles: exploration to investigate regions with high uncertainty, exploitation to examine areas around our current best value, and balance control to regulate the ratio between these two strategies based on the problem and our progress. Expected improvement, or EI, is the most widely used acquisition function and our recommended starting point. It calculates the expected value of improvement over the current best observation. EI naturally balances exploration and exploitation, making it well-suited for most optimization problems. The parameter xi allows fine-tuning, though values between 0.01 and 0.1 typically work well. EI is less prone to getting stuck in local optima compared to more greedy alternatives. Probability of improvement takes a simpler approach than expected improvement. It calculates the probability that a point will improve upon the current best value. However, pi has an important limitation. It only considers whether improvement will occur, not the magnitude of that improvement. This makes it more conservative and exploitation-focused, which can lead to getting stuck at local optima. For most practical applications, EI is the preferred choice. Upper confidence bound, or UCB, offers explicit control over the exploration-exploitation trade-off through its kappa parameter. The formula simply adds a weighted uncertainty term to the predicted mean. With kappa around 0.5 to 1, the algorithm focuses on exploitation. Values of 2 to 3 provide a balanced approach, which is recommended as a default. Higher values like 5 to 10 push toward exploration, useful when you want to thoroughly investigate unknown regions. Thompson sampling takes a fundamentally different Bayesian approach to acquisition. Instead of computing a deterministic acquisition function, it samples a function from the Gaussian process posterior and selects the maximum of that sample. This randomness provides natural exploration and makes Thompson sampling theoretically optimal in terms of Bayesian regret. It's also excellent for parallel experiments since different samples naturally suggest diverse points to evaluate. Knowledge gradient and entropy search are advanced acquisition functions for specialized scenarios. Knowledge gradient looks ahead to predict how much our understanding will improve after taking a sample, making it particularly valuable when experiments are very expensive. Entropy search focuses on reducing uncertainty about where the optimal solution lies. Both methods offer theoretical advantages, but come with significantly higher computational costs, often requiring approximation methods for practical use. When comparing acquisition functions on the same optimization problem, we typically see that EI provides reliable performance across different scenarios, which is why it's recommended as the default choice. UCB offers flexibility through parameter tuning, while Thompson sampling achieves theoretical optimality and works well for parallel experiments. Pi tends to be more conservative and may converge more slowly. Random search serves as our baseline to confirm that Bayesian optimization indeed provides substantial benefit. Here's a practical decision guide for selecting your acquisition function. Start with expected improvement as your default choice since it works well in most cases. If you find exploration is insufficient, switch to UCB with increased kappa or try Thompson sampling. If convergence is too slow, consider pi or reduce the xi parameter in EI. For parallel experiments, Thompson sampling or batch UCB methods are excellent choices. When experiments are extremely expensive, knowledge gradient may justify its computational overhead. Let's summarize what we've learned about acquisition functions. They control the fundamental exploration versus exploitation trade-off in Bayesian optimization. Expected improvement is your best starting point for most problems. UCB gives you a direct knob to control exploration through kappa. Thompson sampling is theoretically optimal and excellent for parallelization. In the next chapter, we'll tackle multi-objective and constrained optimization, learning to handle trade-offs between competing objectives and safety constraints in real process optimization.